All right, so this one, and this is more along the lines of what you'll be given. It's already given in a convenient form, so I don't have to solve for dy dx. I could perform my substitution right off the bat. So I know y is equal to vx, and dy dx, also the same as y prime in this context, would be v plus x dv dx. All right, so I can swap out the y prime for all of this. So v plus x dv dx would be equal to, and then I could replace all my y's with vx's. All right, so we're looking at, let me do that in black. X cubed plus the equivalent of y cubed, x, the equivalent of y squared. So the equivalent of y is vx. And you'll see in a sec, this is shockingly simple by comparison. So we're looking at x cubed plus v cubed x cubed over v squared x cubed. What's happening on the right-hand side of this differential equation, what happened on the right-hand side of the last one in this step, I mean, it was like an hour ago, so you probably don't remember, but you have that common x that canceled out. If that doesn't happen, then either it's not a homogeneous differential equation, which would be a problem because I said solve the homogeneous differential equation, or you did something wrong, all right? In this case, we're looking at 1 plus v squared, v cubed over v squared. So v plus x dv dx would give us that. If I subtract off the v, I get x dv dx is equal to, I just need to get a common denominator. So multiply top and bottom by v squared. And what do I get? Cancels, yeah. So I have a v squared on the bottom, I have a 1 on the top, and so my differential equation in differential form would be v squared dv. So, of course, it would be 1 over x dx once you divide both sides by x, because, you know, that's just obvious. Actually, that little snafu, when correct, is going to make life a little bit easier, because polynomials seem like they're all well and good, but when you have a log or an exponential in your antiderivative, the math tends to be a little bit nicer in the cleanup process. Okay, so we're looking at 1/3 v cubed is equal to ln of x plus c. All right, so we have a couple of choices at this point. One choice would be, do I want to swap out the v? Because we know that if y is equal to vx, that v would be equal to y over x. So we can make that substitution right away and then work with it. Or we could do some cleaning up and then from there make the substitution. Right? It looks like if we're going to do some cleaning up, the only thing that we're going to be able to do is account for the log here. So it seems like maybe the substitution at this point is probably the way to go. So that's what I'm going to do. I'm going to replace the v with a y over x. So that's going to be y cubed over 3x cubed is equal to ln of x plus c. Now I could multiply to clear out the 3, but then I'm introducing a 3 to the natural log. I don't know if I want to do that yet. All right. Ultimately, what I want to do is solve for one variable in terms of the other. Which variable do you think it's going to be easier to solve for, y or x? Y. Yeah, and that's because we have two instances related to the x, to be able to isolate just a single x out of that, it seems like it'd be too challenging, all right? Or maybe it's not that bad, I don't know, but it's not going to be as easy as getting the y alone. So I'm going to multiply both sides by 3x cubed. In which case I'm essentially clearing out the 3 anyway, but along with the x cubed. So y cubed is equal to 3x cubed ln of x plus cx cubed. All right, and that's because the c will absorb the 3, but not the x cubed. Right? It absorbs constants, but that obviously doesn't absorb variables. Right? That's, I mean, if you had separated the steps, multiplied through with the 3 first, the c would have absorbed the 3, and then if you multiply through with the x cubed, it would not have absorbed that. So, yeah, consolidate your constants always, right? Unless you're actually solving for the constant, which is a different story. Now, at this point, we have x cubes everywhere. This doesn't look like a conic section. Well, we don't have x cubes everywhere. We have x everywhere. It doesn't look like a conic section. It doesn't look like anything that has a particular standard form that I'm familiar with. So the best that we can do is take the cube root of both sides and call it a day. All right, so y equals the cube root of 3x cubed ln of x plus cx cubed. And that is the function whose derivative is equal to that. So, you know, just flash back to like first semester, or taking derivatives, if I give you that bad boy in the implicit differentiation unit. That would have been something. That would have been like the whole test. Like take the derivative of that. Nah, it wouldn't have been that bad, but it would have had chain rule, product rule, and then you would have to simplify it pretty significantly. You know, so. But in this case, I mean, really, if you look at it, the ugliness aside, the math wasn't that bad, because the part where you persevered through your substitution paid off in that you came up with an integral or a differential equation that was easy to integrate, very easy to integrate. So really, substitution, a little bit of calculus, substitution cleanup. All right. So really, the only teensy tiny step of calculus is happening from here to here. I mean, you could count this, I guess, but you could also consider this prior knowledge, because you do it once for question 1. It's the same relationship for question 2, 3, 10, doesn't make a difference. All right. So we have some gaps for those of us who weren't here yesterday. So let's see if we can fill those in now. So what we're saying is that we have a function, a homogeneous differential equation dy dx is equal to 2x plus 3y equals x. I'll just give you the short version. This is not a proportional relationship, right? Which means that we can't find the antiderivative using the separation of variables technique, right? The idea of getting the x's on one side, the y's on the other, and then integrating. We can't do that. All right, so what we do is we create a new relationship between x and y, a proportional relationship where v acts as a function, or v is a function that acts as a proportionality constant, quote unquote constant, because it's not really constant, it's a variable function, but it acts as a proportionality constant between x and y. All right, so if you think of y equals 2x, for example, as being proportional, anything that goes to a linear function that goes through the origin is a proportional relationship, right? So the proportionality constant there would be 2, because double one you get the other, all right? You get a proportionality constant of 1/3, you can have it of pi, whatever. Here we're just saying we have a proportionality function of v, all right? So we're defining a new function that allows us to morph x into y, all right? If you can do that, then you have a proportional relationship. The benefit of that is that we can do a substitution of variables and get a new differential equation equivalent to the original but will be anti-differentiable based on the separation of variables technique. All right. So in order to do that, we need the derivative of this, dy dx, first, times the derivative of the second plus the second times the derivative of the first. This guy is the same as dy dx, so that's our first substitution. It's funny, I said I was going to give the short version of the explanation. I'm pretty sure I gave a lengthier explanation just now than I did yesterday. Our second substitution allows us to replace y with vx. The idea again that I'm replacing all my y's, and so basically a function that's containing only y's and x's, differential equation with y's and x's, will now be a differential equation with v's and x's. Right? And this should be a proportional relationship. And you'll know if it's proportional if you go through the process and you end up with some set of variables that you can't separate, right? That being said, I'm not going to trick you on the test and say solve the differential equation and let you guess. When it's homogeneous, I'm going to say solve the homogeneous differential equation. So you're using this particular technique when you see that word, all right? And the reason why I'm doing that is because I haven't really gotten into, I mean, I showed you the rule on the previous page, but I haven't demonstrated how one would determine whether a differential equation is homogeneous to begin with. So you're not on the hook for that knowledge, you're just on the hook for finding the solution once you know it is homogeneous. All right, so if you clean it up, you can see that we have a common x everywhere on the right-hand side. So kill it. So 2 plus 3v, v plus x dv dx, subtract off the v, I'm just consolidating variables, so I'm looking at, so this cancels, x dv dx is equal to 2 plus 2v, much simpler than what we started with. All right. I have a GCF on the right hand side, worth taking out, I think. I'm going to separate my variables now. I want x's to the right, v's to the left. So I'm looking at 1 over 1 plus v. I'm going to leave the constant on the right, the constant coefficient of 2. dv is equal to 2 over x dx, because you have to divide both sides by x, apparently. So pretty not bad, I think, in terms of something that you would need to anti-differentiate. I mean, you went from impossible to, whoa, this ain't bad, I can do this. What's the antiderivative of 1 over 1 plus v? Antiderivative of 2 over x? 2 ln x plus c. Oh, I didn't even know I could, oh, you can't even see my toolbar here, but I didn't know I could move my toolbar, and I just moved my toolbar. It's an exciting moment for me.
How many years has
It's been about 3 years.
It's like when I
3
discovered
years of
the
me being
movie
like,
Doctor.
oh, I'm out of room because of that toolbar. Hold on. Let me just move everything over for a second and then write it and then move everything back. So now I apparently don't have to do that anymore. This is what happens when you're self-taught. So this is the same as saying, I'll write it in all its gory details. Oops, get in there. Oh, jeez Louise. I wanted to write gory details, and I didn't write the gory details. I guess I didn't really need it on the right-hand side, but I just wanted to emphasize that you do have options, because in both cases you have a base E, which means in both cases you can convert to exponential form. The one thing you can't do, and this happens pretty frequently, I'm trying to think, I think it happened on was it the exit ticket? Or maybe it was a test, I forget, but it happened fairly recently. So you can't forget the plus C, and we know that, right? That's hugely important. Right? It happens to me sometimes. In this context, if you forget the plus C, everything falls apart. Because if you forget the plus C, you have logs on both sides of an equation. You might think, all right, drop the logs. But you can't do that because the plus C is there and the C doesn't have a log attached to it. So you would need to consolidate that in. Now, when it's in this form, if you write it like this, you can think, all right, well, maybe I want to make this my base E and revolve everything around that, or maybe I want to make this my base E. It gives you the option to solve your equation for X in terms of Y, or in this case V, or V in terms of X. All right, so just being aware of the fact that you have multiple base E's to play with here, it allows you to solve for one function in terms of the other. Because remember, you might have a parabola as your final answer, but it could be a sideways parabola, in which case it's more convenient to write it as x equals y squared.
Why can't you get rid of the logs by raising both sides to E? Right, you know what I mean? Put an E to the both sides.
You can do e to the both sides, and then when you do that, you're going to have to break this up first.
Yeah.
I mean, you'll have to clean all this up.
E to the C, which is just C.
So you'd have c e to the log, to the natural log of x squared, so c x squared. So it would clean up. It would be fine. But if you don't put the plus c in there, then all you get is the 1 plus v equals x squared. And you lose the constant completely, and chaos. Chaos ensues. Chaos? So e to the 2 ln, once I made my decision to use this as my base e, I'm going to write the other one in the ordinary form. All right, so this is really c e to the ln of x squared equals, I'm going to write it all with the absolutes until this very next step where I'm going to drop all the absolutes with justification. Again, with justification. Don't do it too soon. Right. The presence of the c here allows you to drop the absolutes on the 1 plus v. The presence of the power of 2 here allows you to drop the absolutes on the x within the natural log. All right. So that's your license. They don't just disappear. It's a common misconception, a disgusting one at that. All right, not done, almost done, close to done. You kind of feel like you're done. If this were a multiple choice, you'd be like, choice C, got it. Of course, it would be a trick question because we didn't put the answer in the appropriate form. So V, again, y equals Vx. So V is equal to y over x. Clear out the x, and we will be looking at cx cubed. Well, I'm going to subtract the 1 and multiply by x, so minus x equals y, or y equals all that. Sorry. Needed that.